how do you describe the spectrum of electromagnetic radiation given off by an object such as the sun? Because classically that couldn't be done. And that's where we're going to talk about the ultraviolet catastrophe. And then we're also going to show how Max Planck, with what he thought to be a mathematical fudge, actually turns out not only to explain it, but then subsequently was picked up by Einstein for the photoelectric effect and shown to be not just a mathematical fudge, but a physical reality that light ultimately comes in packets of energy called photons. Right, so let's just go over the fundamentals. As it says on the slide, every single object, essentially every single object, except those at absolute zero, I guess, are giving off, every single object is giving off electromagnetic radiation. So don't be confused, we're not talking about the fact that we're seeing reflections of light in this room, but if you were to switch all the lights off, you wouldn't see anything, but the objects are still giving off electromagnetic radiation, just happens to not be in the visible part of the spectrum. The sun, though, gives off radiation, not only in the infrared and many other wavelengths, but also in the visible part of the spectrum. And the point is, the spectrum observed classically, or observed before we could explain it, relates to the temperature of the object. So the surface of the sun might be 6,000 degrees centigrade, and we know, of course, the sun is very well visible, not advisable to look at it. And then planet Earth there might have an average temperature of 14 degrees centigrade. Again, that though, if we look at that image of the Earth, that's just showing reflection of sunlight. To actually consider what is being given off by the Earth, then you'd better look at the kind of dark side of it, the one that's not being irradiated by sunlight, and then you don't see anything. There's apparently no glowing going on, but in reality we know there is emission of electromagnetic radiation, even from the dark side of the Earth there. Because if you were to get some infrared cameras to take a look, then suddenly, oh yes, the Earth's surface is indeed radiating at least infrared and many other electromagnetic wavelengths. So every object in the universe is giving off electromagnetic radiation. It's just that we often don't see it. With volcanic lava, that is giving off visible light, visible electromagnetic radiation. So you can see lava there about 700 to 1,250 degrees centigrade. And of course, the filament of a light bulb around about 3,000 degrees centigrade, certainly giving off visible electromagnetic radiation. So what we see is this observation that as you increase the temperature of an object, such as a light bulb, lava, planet Earth, or the sun, as you increase the temperature, so the peak emission of electromagnetic radiation also goes up. And so that's why we have the lower frequencies there, not visible, through to the more visible wavelengths. So therefore, the peak frequency of electromagnetic radiation given off by an object is proportional to the temperature of the object. This is what is observed experimentally. And again, don't forget, lambda. This is going to be used a lot in this lecture. You should know it backwards by now, of course, that lambda, wavelength of electromagnetic radiation, is inversely proportional to the frequency, and vice versa, with the speed of light being the constant that allows us to directly equate the two. So low frequency is large wavelength, high frequency is small wavelength. And so we can express that as a peak frequency of a spectrum being proportional to the temperature of the object. We'll see examples in a moment. Or alternatively, using lambda is equal to C over F, we can say therefore the peak wavelength of electromagnetic radiation given off from an object of a certain temperature is proportional to the reciprocal of the temperature of the object. Okay? So let's take a look at a few of those examples in a moment. But just to spell out why that might be, why does every object in the universe give off electromagnetic radiation? Well, because material, of course, is composed of atoms and molecules, and if it's got non-zero temperature, then those atoms and molecules are moving. Atoms and molecules have charge distributions typically, and moving charged particles emit electromagnetic radiation. So simple examples of understanding this might be an antenna for transmitting radio waves. There you've got electrons being accelerated up and down the antenna, an aerial if you like, for the receiver, antenna for the transmitter. And so that's how we get radio electromagnetic waves, by moving electrons up and down quite a large scale object. We're getting frequencies between 20 kilohertz, 3 gigahertz, of the order of meters of wavelength. So that's the more macro scale. Those are low energy photons, EM radiation. If we go down to the more atomic and molecular scale, then again you can get non-uniform distribution of positive and negative charges which are moving around due to heat energy, and therefore they also, as if you like molecular dipoles, are giving off electromagnetic radiation. So it's a very simple concept. Moving charges result in emission of electromagnetic radiation. Okay, so what was the problem then that was being faced by Max Planck? He was interested in the example of light bulbs there, and the filament, and the spectrum of light that you get from a light bulb. And that's related to the problem of explaining sunlight, or explaining, in fact, any of these objects in terms of their EM radiations being emitted. And it wasn't just the peak frequency that's trying to be found, it was actually the distribution of frequencies and wavelengths that are being given off by an object. And these objects are giving off a whole range, a whole spectrum of EM radiation. So again, I'll try and show you an example in a moment. But to cut to where we're going on this quite quickly, in trying to explain this, Max Planck ended up with proposing the so-called quantum hypothesis as, and that's a literal quote, an act of desperation. In other words, when you do the equations, it's like, okay, these are not fitting empirically what we see, but by doing a fudge, or what he thought was a fudge, it actually worked. And as we know, that was actually proven by Einstein to be the case. So let's take a look then to be more clear about this problem that's being solved. So any of those objects typically have what I'm calling a spectrum of electromagnetic radiation. So there I'm showing a spectrum of electromagnetic radiation. So what this is doing is showing us how much EM radiation of a particular wavelength is being emitted from an object of a particular temperature. So this is more or less representative of the spectrum of electromagnetic radiation given off from the sun. And you can see that there is a peak wavelength in the kind of visible range, and then we don't get any energy at this incredibly small values of wavelength corresponding to incredibly high frequencies, but then we get this kind of ongoing distribution of emissions, say, in the radio end of the spectrum. So that's what I mean by a spectrum. And you'll come across that a lot more as you get into Fourier analysis in year 2, the idea of describing spectrum. So what we're going to do, or what they did, was idealize that case, because the sun is not, there's a lot of complications going on there, likewise with a light bulb and lava and the earth and so on. But scientifically, to pin it down to what it is we're trying to explain, there is this concept of what's called a black body. And that, if you like, you can consider as being like a kind of, say, for example, a black cube, which is called black because it's able to perfectly absorb all incoming radiation and also perfectly emit radiation in accordance with what we see going on in the universe. Every object is emitting electromagnetic radiation. Likewise, this idealized black body is emitting radiation, and there's none of the complication of reflections and so on. No, it's all being perfectly absorbed. So there's this notion of a black body, and so we're going to depict that as follows. Incoming electromagnetic radiation would be absorbed and not reflected, okay, of all different frequencies. And then, because it's a black body, because it's a physical object in the universe, it in turn is emitting electromagnetic radiation. And it's the spectrum of emission that we're interested in. And as mentioned, that relates to the temperature of the object. Okay, so emitted radiation has a spectrum which depends on the temperature of the object. Right, again, so that's so the notion of a black body, and very approximately, despite the fact it's not a perfect black body, the sun does have a spectrum comparable to that black body idealized object radiation. So that curve there is the spectrum from a black body, and we'll be describing or showing how that spectrum arises in a moment and how classical physics couldn't explain it. But you can see there that sunlight fits relatively well to that object. So it's a good approximation for understanding a black body. So these are examples of what spectra would look like for black bodies of particular temperature. So we've got 3000 Kelvin. This is what the spectrum of electromagnetic radiation would look like. And then as we go to hotter temperatures, 4,000, 5,000, up to say 6,000 Kelvin, that's something comparable to the sun, then you see that we get this shift in peak wavelength of emission. Okay? So again, this is the amount of radiation on the y-axis, and then we pick a particular wavelength and we see how much of that wavelength is being emitted from the object. And the observation is that peak wavelength drops as you increase temperature. So that's explained by, or fitted by, a displacement law, which I'll show you in a second again. But just to spell it out, hotter is going off to the left there, and therefore the peak wavelength is also going off to the left there. And this is called Wien's displacement law. It's an empirical law based on what we observe experimentally. Again, wasn't very well able to be explained by classical physics. And another, just to fill in the gaps, I don't have to, we're not going to go into this in any detail, but just to observe also that the power, the kind of area under the curve, if you like, goes with the fourth power of the temperature. So the hotter that object gets, not only does the wavelength shift to the left, but also the overall power of electromagnetic radiation goes up as well, which makes sense. If there's more temperature, there's more energy, there's more emission going on. Makes perfect sense. So total emitted energy from all wavelengths, all of the spectrum, is related to the fourth power of the absolute temperature of the black body, that idealized object. Right, so what does classical physics say? So there were these physicists, Lord Rayleigh, Nobel Prize winner in 1904, and Sir James Jeans. They used their knowledge of classical physics to come up with what was called the Rayleigh-Jeans law, which, if we look at that black line on this plot of the spectra, you can see it looks absolutely appallingly bad, because no way does that black line for, say, 5,000 Kelvin, doesn't agree at all with the experimentally observed spectrum, say, of the sun. You might think, so why were they even mentioned? Why did they even come up with that law if it doesn't even work? Well, actually, although it's hard to see here on this example, this Rayleigh-Jeans law for explaining the spectrum of EM radiation does actually work quite well if you go to large enough wavelengths or low enough frequencies. Basically, therefore, what that means is that as we go to shorter and shorter wavelengths, okay, so that's lambda there, so 1 over lambda squared, proportional to frequency squared, as we go to smaller and smaller wavelengths, so the intensity I shoots up, okay? Whereas if we go to very large wavelengths, then the intensity drops down. Okay, so you can see a very obvious intensity proportional to 1 over lambda squared. So that's why we get that very simple curve. And again, it fits well for objects of quite low temperatures, but breaks down when we start considering higher temperatures. So that was a big problem for classical physics. And that's why it was called the ultraviolet catastrophe. Because if you look at this part of the electromagnetic spectrum, the kind of sub 400 nanometer kind of range, this would be the ultraviolet range of wavelengths. So you could have just as well have called this, I would suggest, you could have called it the X-ray catastrophe or the gamma ray catastrophe. Pick any high frequency. Classical physics was saying, oh yeah, the intensity of emission is proportional to the square of that frequency. And obviously, for ultraviolet light, for X-rays, that's very high frequency electromagnetic radiation. and this is shockingly saying the intensity is proportional to the square of that frequency. So that means the smaller and smaller the wavelength of the EM radiation, the more and more colossal the predicted intensity of radiation. So clearly, in quotes, catastrophically wrong. A bit like the Rutherford model, which you'd say therefore should lead to unstable atoms. The electron collides with the nucleus. That's a, if you like, a classical catastrophe. This is a catastrophe in being able to explain the intensity of electromagnetic radiation from a black body. So this is where Max Planck came along with his act of desperation in trying to fix that classical Rayleigh-Jeans law, which was catastrophically bad for high frequencies. And the mathematical fudge that he put together to fix the explanation for the spectrum of EM radiation from a black body, such as a light bulb as an approximation, was to say that light energy comes in quantized units, if you like, discrete packets of energy, which are simply proportional to the frequency of the EM radiation. And the constant of proportionality is what's known as Planck's constant, such as the scale factor h. So the higher the frequency of the EM radiation, that means the more energy is required to produce one quantum unit of light, one photon. The greater the frequency, the more energy needed. So that means an X-ray has much higher energy than, say, an infrared photon, which has much lower energy. Infrared is low frequency, low energy. X-rays, high frequency, high energy. Okay, so let's spell it out. Let's understand why that is so profound, because it looks incredibly simple. It's not even y equals mx plus c, it's not even a linear plot, it's just y equals mx, just one proportional to the other with just a gradient, a scaling factor h. So there we are. The amount of energy needed to make a photon of frequency f goes up linearly according to the frequency. And again, just to spell out what we mean by frequency, this is the electromagnetic spectrum. And what we've been saying is that as objects get to greater temperatures, so the peak frequency emitted goes up, and there we're seeing typical sizes of objects corresponding to those particular frequencies. So buildings are of the size of radio waves, and molecules and atoms and gamma, and a nuclei are more of the size of gamma rays, X-rays, and ultraviolet. Okay, so just to say again what we're claiming here, which is that the energy needed to create a photon of a particular frequency f goes up according to the frequency f with a scale factor. So let's see again what this is telling us then. It's telling us the following, which is important to understand. If there's some amount of energy E, so this is just my way of trying to convey to you how this fixes the ultraviolet catastrophe. What we're saying is if we've got some energy E that we're wanting to express in the form of photons, what does that simple equation tell us? Well, imagine then we were going to use these low frequency photons. This is lower frequency, higher frequency. So let's see if the amount of energy, okay, for creating a photon of frequency f is, if you like, depicted by this amount of energy, then to express that amount of energy E in terms of that frequency photon, we can see we can just create lots of photons of that particular frequency in order to express that energy in terms of photons. If we go to a mid-range frequency, like the next one, then again, we can express that energy E in terms of quanta of frequency f, but you can see as I've tried to add on yet another photon there, it actually exceeds that energy E that I'm trying to express in terms of photons. So in fact, no, I can't make that one. What I can do is use 3 photons, and then I'm falling short of that energy budget, so I guess I could use some of the lower frequencies to make up the difference there. You get the idea. If I go to a higher frequency, now I might only be able to make 2 photons with that energy budget. If I try and do a third one, not allowed, it exceeds the budget. And now, if you were to imagine an even higher frequency, okay, then we don't even have enough energy to make a single one of those photons. And so that frequency, just by this simple expression, that frequency of photon is simply not possible for that amount of energy E, so you don't get any of those photons. So that one's not viable. So the quantum hypothesis is to say that energy E is given by an integer n, so we've got a discrete number n of photons of energy packet size hf. Very simple, but has profound consequences. So as I'm trying to spell out again there, so we can have many low frequency photons, fewer photons of that mid-range frequency, even fewer of those, and don't even have enough energy to express one photon at very high frequency. So how does that rescue us then if we come back to the spectrum of EM radiation given off by a black body? Well, as we know, the Rayleigh-Jeans law was predicting this ultraviolet catastrophe, where the intensity shoots up according to the square of the frequency, in other words, 1 over lambda squared. Smaller wavelengths give more and more amplification of that intensity of emission. But Planck's law, and we'll do this a bit more in the tutorial tomorrow, we'll go into a little bit more of seeing how this does the fix. By using that quantization of energy, so I won't be deriving it here, but by using that quantization of energy, Planck was able to come up with this formula, again thinking it was just a fudge in order to explain those distributions. He came up with this, and that formula arises directly from saying that delta E is equal to HF. In other words, where we've got some energy packet size that goes up according to the frequency of photon being emitted. And so we can see already what's going on then. If the frequency is very large, that corresponds to a wavelength that is very small, then I'm sure you can imagine, with your knowledge of mathematics, exponential of a very large frequency, in other words, a very small wavelength, that denominator becomes absolutely colossal, which means that that intensity becomes incredibly small and in fact reduces rapidly to 0. So we can see mathematically why this fixes the problem. And as you can see there then, we actually get no photons at all if the frequency f is high enough that we're considering. In other words, if we're considering very, very small wavelengths, such as beyond gamma photons, you know, if you can get more energetic than that, then we get essentially 0 intensity of emission of EM radiation. So we'll look in the tutorial tomorrow a little bit more at that expression and how that correlates with Rayleigh-Jeans law for small values of frequency, in other words, large values of the wavelength. Okay? So he used delta E equals HF to come up with that expression for the intensity of EM radiation from a black body of temperature T, which fits the data beautifully, whereas the Rayleigh-Jeans law does not, and the Rayleigh-Jeans law has the ultraviolet catastrophe going on. The take-home message is that by quantizing light energy into packets, photons, Planck was able to explain the experimentally observed emission of radiation from objects at temperature T. If you don't have that quantization, then you end up with a very wrong answer. So this matches the data. Great news. And as we saw in the tutorial on Friday, you can actually measure that Planck's constant by the photoelectric effect experiments, by doing reverse potentials and so on. And that constant of proportionality, in other words, the energy to make a photon of light of frequency f is equal to h times the frequency, that constant of proportionality, it turns up everywhere. So it's energy of photons equals hf. It comes up in quantum mechanics for describing the momentum of particles, relating them to the wavelength. Profoundly, it's as simple as h over lambda. We'll do that next week when we get into some quantum mechanics. And also, hopefully next week, we'll touch on Heisenberg's uncertainty principle. And yet again, Planck's constant comes up in the Heisenberg uncertainty principle.